Okay, here we go. Last time just we started looking into operational amplifier, and we said the first stage of an operational amplifier is a DFAM, differential amplifier, and if you have used the op-amp recently, you have seen that there are two terminals, one they call V minus, the other they call V plus, are essentially the two input terminals of a DFAM. Okay. So we have already done something, but I just want to recollect. So you can see the input to a op-amp is essentially input to a differential amplifier. Now this here shown here, as there is only one output, there is a possibility that it may have two outputs. So call it VO1, VO2, and I can actually take a difference between the two and can get VO1 minus VO2 as my new outputs. Okay. Or I may see I only get one of those outputs, the other is not relevant the way I do as in most op amps, and we say that is my VO. Is that correct? One small thing you must understand, the circuit shown here or the symbol shown here does not have any connection between V0 and Vin except for the capacitances, because there are CGDs and they will give some connection. So there will be poles and zeros associated all the time, even if we do not say they are capacitances. However, in all op amp circuits barring exceptions I will say, there are no internal capacitances CC1, CC2 or CC, or there is no such capacitances present in any operational amplifier. So what is the advantage of such system? What is CC1, CC2 were doing? They were decoupling DC and AC. So the trick here is now what I am saying, that an op amp can also receive DC inputs. Is that correct? Op amp can receive DC input. All other amplifiers we do not amplify DC. What do we amplify? Only AC signals. But it is different from all normal single ended amplifier DFAM is or op amp is, that one can amplify DC signals. Is that correct? That is the major difference between normal single ended amplifier, which are small signal AC amplifiers. So if I really plot the Bode plot for that, what will be the typical gain you will see from here? If I plot gain versus frequency, at 0 frequency gain is not 0 or not falling. So typical characteristics of a Bode plot will be something like this. Even at DC 0 frequency there will be a finite DC gain. Now this DC gain is same as what we say otherwise DC gain. Okay. So that is the major difference we should understand, that in the case of op amps or in DFAMs, even at DC outputs are possible. Is that correct? So in all my analysis ahead, why I am showing you this, I am actually not differentiating too much between small ID, capital ID. So I may use a term like ID, which actually takes care of AC plus DC or only DC or only AC, as if I am having some signal which is getting at the outputs. Okay, is that clear to you? So that is slight symbolization sometimes, because we have been talking single ended amplifiers, small signal ones, and we are very categorically saying small, small, small. We say put ACs only. Okay, here we may see what is the difference. However, normal gain of this amplifier, which is a small signal gain, is still an AC gain, whereas the DC gains are not possible if this circuit acts. What will happen? If there is an input signal between this input terminal, the output, because there will be large gain of an amplifier, the output will go where? Gain times the input, where it will go? Very large value. But the maximum value available to you are what? Maximum minimum? VDD and VSS. So actually the output may become either VDD or VSS, depending on this is higher or this is higher. Is that clear? What's this circuit should be called therefore? I have two inputs. If this is higher, this goes to minus VSS. If this is higher compared to this goes to plus VDD. Comparator. So I can now use the same op amp. If I compare the two inputs, depending on the output, whether it is VDD or VSS, one can declare VDD as 1 minus VSS 0, and therefore it is like a logic block. A two input signals can be compared and the output can become digital 1 and 0, is that correct? This is the advantage of a op-amp over normal single ended amplifier, and therefore we want to know what exactly goes in, how this is possible, and that is why the present thing we have started with differential amplifier. Is that clear why we are so keen? Because every other circuit in future will use op-amp, and whether it is A to D converters or D to A converters or any filters, everywhere we will use operational amplifiers. And since we are going to use operational amplifier, the first thing we must know what it contains and why it gives such a behavior which we can then utilize ahead in systems. Is that okay? So this issue which yesterday or day before yesterday I did not say, I thought I just started DFAM because it was a evening, late in the class, so I thought maybe that time I did not spend time, but you must know my context why I am doing this. I do not do anything here which I do not think I will use later unless I have some reasons to say okay I know it is important but I do not want to use it. Right now I say whenever I do something it has a repercussions ahead, that is why whatever I teach today will be required tomorrow, tomorrow means next. Okay, having shown you the operational characteristics, operational amplifiers. So also one interesting feature about this op-amps is this, which is also interesting to show you, because if I plot VO versus Vin of a operational amplifier, depending on if I can ground this and take a reference, minus Vin also can occur. So I will find, sorry it will cross to 0, there is a range in which for minus Vin or plus Vin the output will be high, linearly follow it, and at certain higher input signal it will start saturating. So even in op-amp there is a limit up to which input swings will be allowed to have larger outputs, beyond which what will happen, they will saturate, and then what is the essentially whenever the output saturate, what is the gain? Gain is 0. Essentially it will never reach 0, but it will be a very small gains will start coming closer to 0, and because of that the outputs will be non-linear, and non-linear if I expand it in a Taylor series or a Fourier series, then I will get different frequency components, omega 1, omega 2, omega 1, 2 omega 2, omega 1 plus minus omega 2, these are called harmonics. Okay, so if you operate somewhere here, not only omega 1 your major frequency output will appear, which will be much reduced because part of the power will be delivered to other frequency components. Is that clear? So one does not want to operate in the saturation, around saturation region, so there is a limited range even for DC, is that correct? It's even for DC there is a limited range in which amplifier will act like a linear amplifier, is that clear? Otherwise it will be a non-linear amplification in which it means that other frequency components will started receiving power. Okay, this fact has to be understood, that even op-amp, I keep saying DC, it does not mean 100 volt I apply and I will get 1000 volts, because if that occurs it would be a great thing, with a small device I can have a generators put everywhere in the houses and I can supply power without any power coming from anywhere else. Such a thing thermodynamics will not allow. So therefore there cannot be such energy creation without any other creation giving energy. So do not believe that it will have infinite ranges, it will have limited ranges for amplifications as well. Yes. No, because linear region is sin omega t term, all sin omega terms will only get amplified. No, it will, as I say, please do not confuse between DC and AC. Okay. AC signals will get all other frequency components. DC signal cannot get, it will just saturate to one DC value on the plus side or the minus side. Is that clear to you? If I have a only DC inputs, either it will go to VDD at the output or VSS. Okay, but if I AC signal overriding a bias voltage, then that AC signal in the non-saturation region, you see, understand how do I write non-saturation? A0 plus A1x plus A2x square, you write the expansion series, x square term means sin square omega t. Sin square omega t means 2 sin omega t minus 1, so 2 omega t term appeared, you take the cube you will get 3 omega t terms. So you can see when small signal AC goes it will give harmonics, DC does not, is that clear? It will give a fixed value of 2 DC values, that is what comparator does, it actually fixes it to a fixed 2 values. So it will enhance by that much gain, whatever DC value input you have into the gain, that is the dV0 by dV in, which is your gain, multiplied by the DC input, that is the output voltage. No, it will not, because in those regions there is no signal, okay, the device is not introducing any harmonics from itself. The device gives you non-harmonic harmonic content because in non-linear relationship the term square, cube, 4 terms occurring, and that only when you have sin omega t as signal, then sin square omega t, sin cube omega t, they will give 2 omega t, 3 omega t and combination of these as the signals, okay. So only ACs will give this kind of, okay. We looked into yesterday that a differential amplifier can be in the MOS differential amplifier or it can be BJT. I will not do I may be at the end of this DFAM, I may just show you a bipolar DFAM. I may solve something, the similar thing as happened in MOS, but other things you read in the book which I officially said Cedra, Smith and me, okay. So read there the other parts of bipolars, okay. I will only do MOS parts and will expect you that you read bipolars, okay. If you have an issue that okay it is not same and it is not correctly coming and you do not understand, that part we may do again in the class, otherwise we assume that techniques are same and therefore can be applied to any other blocks as well, okay. So we said we define 2 signals, if V in 1 and V in 2 are my inputs to a differential amplifier which has 2 input ended it is not single ended, it is a 2 inputs. Then we define signals as VID, which is subtraction of the V in 1 and V in 2, whereas there is another signal we call common mode, which is the average of the two, V in 1 plus V in 2 by 2. Now as I said yesterday, the DFAM has the advantage that noise normally is common mode. What does it mean? On the both terminal noise has same sense, okay, or same amplitudes, and the DFAM has the biggest advantage that it rejects common mode signals. That means anything which is common, output does not show that, is that clear? So if there is a noise overriding on your signal and if it is common mode, which will normally will occur, then the output will not show noise amplification, is that clear? That is the advantage why DFAMs are or op-amps are used, because it rejects other signals which is common mode. And the word there we use is what? Common mode rejection ratio. How much it can reject is the criteria of a good op-amp. Large CMRR should be good, but this word will come back and say no, don't go 125 dB CMRR or 200 dB CMRR, because if that happens something else will be hurt heavily, your bandwidth may not be there, phase will not be occurring, so there are issues. But larger the CMRR, larger is the or rather better is the circuit for operational or DFAMs, okay. So minimum DFAM CMRR should be around 80 to 85 dB, should exceed not more than 120 dB, but around that 120 is okay, I am not saying it is bad, but never try for CMRR of 200, okay. In fact theoretically the CMRR may come as infinite, how much? Theoretically ideal situation CMRR is infinite, okay, but there is nothing ideal in the world, so CMRR is never infinite in the world, okay. So we will see why that does not occur, okay. So this is just what we did just the other day. Okay, we said a DFAM has 2 single ended amplifier in which their sources are connected and there are 2 resistances, there are 2 single ended amplifiers. Assume RD1 is equal to RD2 equal to RD, then this is the circuit which we call the differential amplifier or DFAM in short, DFAM, okay. This ISS is the biasing current, in MOS it is normally called ISS, in bipolar they call it ICC or just I, okay. So if you are doing otherwise just look, they only make capital I, that is it, okay. VSS is the negative supply. So op amps will always are having dual rail power supply. What is my dual rail? Plus VDD and minus VSS. But there are single rail op amps also available, that is only VDD. Is that clear? I am not trying to say that single rail op amps are bad or worse, of course bad, they are worse than dual rail power supply based op amps. Okay, this has, I repeat again, has anyone started looking why negative voltages are relevant in analog, whereas in digital we never look for it. Think of it, what is the advantage I get? Difference wise still I am VDD minus VSS minus VS, that is the net voltage. If it is 2.5, 2.5, it is 5 volts. So I could as well put 5 volts, single supply. If I have 5 volt supply, I can make 2.5 minus 2.5, which is also 5, or I make 5 0. But why I do 2.5 minus 2, and normally we also see that the same opposite is occurring, 2.5 minus 2.5, not 3 and minus 2. Okay, that also has some disadvantage. Okay, so think of it, maybe at the end of op amp I will say why dual rails. Dual rails are very relevant. Okay, some partial answers I gave someone who asked me here, but I will give them more detail later. Let us say the first case, DFAM, please remember I again show this, Vin1, Vin2 are the two inputs and the common mode is Vin1 plus Vin2 by 2, difference signals is Vin1 minus Vin2. Okay. Let us say DFAM has same inputs at the both end, Vin1 and Vin2, is that correct? So how much is difference? 0, but what is the common mode? Vin plus Vin by 2 means Vin, is that correct? Vin1 plus Vin2, if they are equal, that means both sides the signals are same, Vin. Okay. So Vin1 is equal to Vin2, and since they are connected at the gates, Vg1 and that is equal to Vg2, is that correct? This is the common mode part in that. Now you can see from here in our circuit, can I show you a little bit, the source of both, call it M1, M2 for future, source of this both transistors are connected, common, they are same. So what will be the potential on both sides, will be different or same? Same, because at any node there can be only single voltage, that voltage I call Vs, source voltage, is that correct? So how much is Vgs for this? Vn1 minus Vs, how much is this? Vn2 minus Vs is the Vgs for M2, but since Vn1 is equal to Vn2 and call it Vn, both transistors have same Vgs, is that correct? If they are same devices of same threshold, Vgs minus Vt is also same. Let us say ISS is so balanced that they give sufficient current so that both devices remain in saturation. So what is that means? This current half will come here, half will come here, because both are Vgs minus Vt is same for both devices, is that correct? Because if they are equal, Vts are same, the half current must flow through them. That is exactly what she said. Yes, we do not apply, it comes. If I apply Vn1, Vn2, there will be a possibility that they may be equal at a point, is that clear? So common mode is a not necessarily, of course noise is essentially the common mode signal, isn't it? Actually I will show you the game there, how do we, given a different signal it can always be represented as sum of common mode and difference mode. Okay. So we say Vg1 is equal to Vg2 is equal to Vgs1 equal to Vgs2, and we define Vcm as Vn1, Vn2, Vgs1, Vgs2, and the source voltage is of course Vgs, Vcm minus Vgs. Okay. What is, why it is say, sorry not Vgs, actually it is Vg, Vg minus Vs is the signal there, Vgs. Okay. So we say Vcm is, source voltage is Vgs minus Vt, is that correct? Vgs minus Vt is the drop across that, that is we defined as VOV, Vgs minus Vt we defined as VOV. So we substitute there, since Vgs1 is equal to Vgs2, one can always say that ID1 plus ID2 are equal if they are half situation, if they are equal, But even if they are not equal, the issue now, please take it, here they are equal, is that correct? Even if V in 1 is not same as V in 2, one may have larger current than the other, but the net current will be how much? The ISS, because that is what you fixed. So sum of ID1 plus ID2 will always be equal to ISS. If they are equal, so which each will be ISS by 2, if not equal, one will have a larger value than the other. This is what DFAM allows, okay. If they are equal, half. If they are not equal, one will draw larger, other will be drawing smaller, but sum total will only come to ISS independently. This is exactly what we are looking into. Okay, Vg minus Vs is Vgs, but Vs is common to both, okay. So is that clear to you? Because the subtraction is same for both, is that correct? Same, because Vs is common voltage, okay. Okay. So if I do that, if ID1 is equal to ID2, it is ISS by 2, but we know the current in the this is half beta n dash W by L by 2 Vgs minus Vt square. ISS is then represented as VOV square, so VOV is 2 ISS upon beta n dash by W by L. At what point, where is this defined? When the current is half in both circuits, is that clear? ID1 is ISS by 2 and ID2 is also ISS by 2. For this condition VOV has been defined. Normally we do not define that way, we define only normal, but in this case for the common mode ID1 is equal to ID2, and at that condition the VOV is defined by 2 ISS upon beta n dash into W by L. Okay. थोड़ा मैथ्स, ये इसको इधर ले जाओ, इसको इधर ले जाओ, ये आ जाएगा, okay. This is half beta W is W by L, but the current essentially, this is ISS. Please remember what is ISS. If one of the device is working, it is beta n dash by 2 Vgs minus Vt square. If it is half current, half the current will go to ISS by 2 on one side, ISS by on the other side. I agree, what you are saying I fully appreciate, but okay, call it like this to say that, okay, if one of the device is operating, normally we define that my VOV, okay, one of the transistors. Since it is half the current for individual cases when equal currents are there, we now define a new VOV which is related to half currents. ISS का तो पूरा formula है, आधे के लिए आधा आधा कर दिया उसका, is that clear? And for that we define new VOV. That is for single transistor with one drive completely driven by it, but since it will be half, then I say for that half we define new VOV. This is a, I agree, we need not have defined, we should have kept normal VOV also. It would have come additional 2 terms somewhere there, fair enough, nothing goes wrong, is that clear? It is only a nomenclature which Cedra Smith has been using, and I thought since you are going to read that book, I should follow their nomenclature, otherwise I myself would not have done it. I agree with you. What we are she is saying, this why this half is coming here? This half is essentially, this is a normal IDS current for any transistor. So I say if only ISS is flowing in one transistor, half beta into Vgs minus Vt should have been the current, is that correct? But since each is driving only ISS by 2, I am just dividing it by half both sides. No, that is what I am saying, you know, when one transistor works, if that is what say the definition was something like this, that if only one of the two transistor works, the other does not, all the current will flow through one, and that I call half beta n dash W by L into Vgs minus Vt square, whatever Vgs for that transistor. Is that clear to you? That is the current it will flow. Now you say if it is half, then the Vg is equal, still equal, okay, but the current is now shifted half. So I divide the current by half old one, okay, whatever we used earlier, आधा इधर आधा इधर. Okay, we will come back to ये modify किया जा सकता है, don't worry. This is what they have done it. I would have agreed, I would not have done it, but since they are following this method, I thought I should give you their method. You are perfectly justified. So what is Vd now? Can you tell me Vd? Okay. So what is the drop at the drain? The resistor drop Id into R is the VDD minus, that should be the output voltage. So VD1 is equal to VD2 equal to VO1 equal to VO2 is VDD minus ISS by 2 times RD if RDs are equal, otherwise they may also not be same. Then what is the output? Subtraction of VO1 and VO2, 0. If they are 0, what do you expect the gain? If the output which is defined by me as VO1 minus VO2 and input is how much? Common mode Vin equal to Vin1 equal to Vin2. So what is the common mode gain? What is the common mode gain? Output voltage divided by common mode signal. Output voltage is how much? 0. VO1 minus VO2 is 0. So the common mode gain is 0 in the case of differential amplifier. That is what the rejection word is clear to you, that any signal which is common will not get amplified at the output if the difference of output is collected. Is that clear? If the difference is collected, VO1 minus VO2, there is no gain for the common mode signals. Now question is this valid statement? Because it is not true, because the way we will define latter, which we just now said word CMRR, is essentially called ADM, difference gain upon common mode gain. Okay. So what is CMRR for this? Infinite, and as I say ideally, that means this condition which I put is an ideal condition. ACM is 0 is an ideal condition. Why it does not occur as 0 and how much it will occur, we will go and actually evaluate the ACM. Is that correct? No, it is not 2, 4, it is equal. In common mode the signals are same. Vn1 is equal to Vn2 is only common mode. Correct. So the correct, if the two signals has a component which is difference possible, they will get amplified, but the common will reject itself. Yeah, but we already said we will always operate in a linear mode. That is what day 1 I started. We will see to it your biasing is such and Vn is such restricted that we are always in the linear mode. That superposition is guaranteed by us. Is that correct? That is what I started with you when I showed you that I am always going to stick in this. Is that clear? And that condition is still valid. If your doubt is doubt, so let us clear the doubt. If this is for any transistor, this is my Vg and this is my Vs. If this is my Vg and this is my Vs. So what is VGS for you? Vg2 minus Vs is VGS2, VGS say Vg1 minus Vs is VGS1. If Vg1 is equal to Vg2, VGS1 must be equal to VGS2. That is what I said. Yeah, that is because the difference between the two is same. What I said is, okay, oh sorry, I made a mistake. I should write Vg1 minus Vg2 is always equal to VGS1 minus Vg2. Yeah, I agree with you. Yeah, your point of view is valid. What I said maybe I am wrong. What I essentially saying, what she is saying is that the difference is equal. VGS is equal to VGS. Yeah, you are right. The idea was that Vs, since it is common, this it will also get as if close to 0. The reason why I said for AC, this potential will go to 0. So that is for that AC part, yes, they are equal. For DC, they are not. You are right. Yeah, you are right. VGS1 is equal to VGS2. Okay, perfectly justified. Okay. Normally our assumption in this that all transistors are identical, all resistances are identical and the current source is ideal current source. Please take these 3 conditions. In deriving this thing we made 3 possible this. One is the 2 transistors are fully identical, the W-bials are equal, the thresholds are equal, okay. Second condition we said RDs are exactly equal, and third condition say the current biasing current source is ideal. Is that correct? If there is a resistance there may have some issues, okay. three conditions are called ideal conditions. Under that state, yes, the common mode gain will be infinite or sorry 0, and therefore CMRR will become infinite. Please take three conditions. Is that clear? Three conditions. Okay, I should say third one also, and ISS is ideal current source. I will come to this very soon and I will show you why I said so. Okay. Otherwise the current in both VO1, VO2 will be different for both, even if the currents are same. So essentially VO1 minus VO2 will never be 0 then, even for half currents. If RDs are not equal, then the drop across them are not equal, so the subtraction will not be 0. So if that is what I say, since if they are not equal, that means there will be some difference voltage. So common mode will not go to 0, there will be some finite value. Is that clear? VO1 minus VO2 will not become 0, then it will have some value which will be smaller, because RD1, RD2, even if they are not equal, they may not be 2 for 110K, 100K nahi hoga, 10.05K, 10.02K. That is because of the process with which resistors are made, one cannot guarantee. But how do we say we guarantee on these circuits? Why did I say in integrated circuits this is doable, discrete nothing is doable. Is that correct? In discrete I can never guarantee RD1 equal to RD2. कितना भी short resistors लेके आओ, since most of the meter given to you to monitor is you are only using ohm meter, उसका least count ही इतना कम है, ज़्यादा है कि 10.0 के आगे कुछ वो correctness दे ही नहीं सकता है. So you always feel both are 10. Okay. Essentially if you have a good measurement system, you will find they are not equal, and if they are not equal, even with everything else VT equal, firstly VT will not be equal for two transistors. Okay. So in which case what is going to happen is VO1 minus VO2 will be some finite quantity, which means ACM will be some finite small quantity but finite quantity. Ideally it should go to 0, and therefore CMRR rejection should be almost infinite. Okay. How good is this number is what we are going to see. Okay. As I say, how much I said you, please remember this is range you must work in real circuits. 80 to 120 dB में ही CMRR होना चाहिए, उससे बड़ा किया तो क्या होगा, उससे कम किया तो क्या होगा, ये सोचने लायक है. Okay. Is that okay? These numbers are only for those who are someday going to work on integrated circuits designs. For this, these numbers are crucial. Okay. Okay. There are two. These are two. This is not the ideal way I am explaining, but just there is another term which all op-amp people use, and they call input common mode range. What they call is ICMR, and this is essentially coming from the DFAM itself. So shown here. Is that word clear? Input common mode range. So what does that mean in your mind without seeing this? What does that I mean? Input common mode range. So what is the maximum and minimum common mode voltage which are possible, which will allow device to operate and saturation, both transistors to remain in saturation and in linear mode. Is that correct? If that occurs, we say this is the maximum VCM and another is minimum VCMs, you must work within this. So what does that mean? If the noise overrides this value, then it will show you at the output as well. Is that clear? So there is a limited range in which VCM can be operated. Okay, here is some tricks on that. ये एक जनरल मेथड मैं आपको बता देता हूँ, ये इसके लिए ही नहीं है, पूरे सर्किट वालों के लिए है. Whenever I want to get a maximum value which is occurring at the input, you always go from VDD. You calculate from VDD down. Is that correct? Whenever I want the minimum value, you should always calculate from ground or minus VSS towards the input. Is that point clear? These two terminologies you take independent of this, which I am going to use. I repeat, for the maximum value you come from this, for the minimum value you come from this. Whenever any maximum values at input or you are trying to see, for maximum start from power supply and for the minimum start from minus VSS. इधर से ये कितना और इधर से, that means maximum value is decided by VDS of this and RD of this. minimum value is decided by this as well as the VGS of this. Is that clear? So these two values are different from each other, and one gives max, other gives minimum. This is true for this circuit, true for any circuit in which such calculations are to be performed. Is that correct? I repeat, for the max start from higher end to the point where you want, and for the minimum go from the lowest end to the point where you want to come. This is the standard method which should go here, independent of what I am going to teach now. Okay. This I keep saying it because you should know the way tricks we follow later. Okay, so we say VCM occurs when M1 and 2 are the edge of saturation. When both transistors are at the edge of saturation, we say that is VGS minus VT is equal to VDS. So we say what is common mode at the gate source voltage. Okay, so VC max minus VT is equal to VDD minus ISS RD, half the current, both transistors are half. VC maximum minus VT is equal to VD, is that current? What is this value? Again see the circuit. I just now said VDD minus this drop, you are here at the drain, please look at it, VDD minus this drop, you are at this end, then you want actually VGD. What do you want? To reach here you need a VGD, but if you say VGS minus VT equal to VDS, I can get VGD, which is VT. Is that clear? So I can get this into VT plus VT as, I repeat, if this is at the saturation, I am now saying, okay, that expression anyway I am showing you, VC max minus VT is equal to VDS. Okay, at that point it is at the edge of saturation. VGS minus VT is equal to VDS is the edge of saturation. So if I substitute this, and that voltage must be equal to VDS, which is VDD minus this. So if I equate them, then I get VC max is VT plus VDD minus ISS by 2 into RD. Is that correct? This is the maximum input common mode possible. What is the condition? It will, if you go beyond that, this condition will get violated. Is that correct? Device will enter which region? Linear region, and then your whole linearity will be lost. Is that correct? Is that point clear? So that condition which I put is the device should remain in saturation, but the maximum will come when it is at the edge of saturation. Is that correct? So that is the condition. Now coming to the minimum side, from where I should take minimum? From the source side. The minimum occurs such that Vs, which is the source voltage, please remember source voltage is, ये जो source voltage है, ये इस current source कहाँ कैसे बनाते हैं current source आपको पता है? How do I make a current source? If I use a transistor, put a proper VGS and this, and I see to it that the current is constant here, okay, is that clear? Then it becomes a, and what is the other property of a current source? Not that the only current is constant, our source is close to infinite, okay, that is the condition of a good current source. So there is a voltage drop across this transistor VDS of the current source. So this Vs is essentially Vs minus Vss is how much? The VDS of the current source. That name I have given as VCS. What is VCS? Is the current source voltage drop. Current source, not ideally what should be the voltage drop? 0, okay, but it is not ideal, so it should be some drop across the VDS, which is the VDS of that transistor is the VCS number I gave you here. So the VDS for the current source is Vs minus VSS, please take it, this is minus of minus, that means it adds in fact, is that correct? Vs minus of minus means actually that voltage is adding to, that is offset plus value it will give. So the Vc minimum then is, okay, first you remove this Vt, this, it is this VG, please take it, this voltage, please take it what I am saying, the minimum value is VGS plus VCS, is that correct? Is that clear? This value plus this value is the input, is that correct? So if I do that, I write VC minimum is VGS plus VCS, VCS minus which is equal to minus VC, just now I wrote common source voltage VDS for that. So we say, and I added VT and subtracted VD. Why did I do that? Just to make it some VOV term appearing there, okay. Actually this VT was not there, but I just added and subtracted. So I get VOV plus VT plus VCS plus VSS, okay. Is why it is minus VSS, but it will become plus, why? VSS is negative quantity. So this is called VC minimum. So what is the input common mode range then? What is range called? Maximum minus minimum, is that correct? What is the range? Max minus min. So VC max minus VC min is the input common mode range. What are the two conditions it is satisfying? One is device is at the edge of saturation, it goes at best to the edge of saturation for maximum input signal to allow in common mode, okay, and it goes to the minimum of that value when the current source is a constant current source. Anything violated there will not allow that VDS to remain in saturation, which means the device will then, it will not give you a constant current to you, is that correct? That means the bias point will shift away, is that clear? And therefore these are the two swings voltages in which common mode signals are possible to be amplified, okay. The current source will not act like a current source, because that VDS will be then smaller than VGS minus VT for that current source. So device will enter linear mode, so it will act like a resistor there, okay, and very small resistor. If it is large resistor, there is no problem because it is still a constant current source. If it becomes smaller resistor, that is the issue, and then we will say CMRR will go to 10 dB, okay, that is what happens. Current source is not coming from somewhere else, it is a part of the DFAM actually, and the way it will create it, I just showed you how will I going to create that, okay, there will be a transistor sitting there, okay, is that okay? Okay, so having shown you, so ICMR is VC max minus VC min. So ये subtract करो, that is the range in which, so many times when I design an op-amp, one of the specs they give me, this is the ICMR, okay, this is the ICMR. So I actually from there I know what values I have now value I can get out, so that the ICMR is within the range given to me. So they may give you -2 to +2 or +3, okay, so I must now work within this range. So at no time the device WBILs and the currents I use should go beyond these values to make device going out of this range, is that clear? That is something one has to design. We take care of ICMR day one because that is the limit I always see, okay. Okay. The current source must remain current source, that means it must saturate there. But that is always, because that ISS, if it comes out of it will not, as long as that current is constant, that device is in saturation anyway. Even at the edge of this, ISS is still flowing, that will still, ISS by 2 will still make M1 saturated. But that as soon as this is conditioned, that will automatically get satisfied. We chose ISS such that M1, M2 gets satisfied, half the current will make both saturated. As long as you are on the edge, you are still satisfying the upper condition anyway. If you get out of that, that the current source does not remain same current or much smaller, then both will come out of saturation anyway. Not only this, the upper one will also, and that is why I say we say input, it will come out of it, okay. So device will not in the linear mode anyway, is that okay? Okay. To some extent yes. Okay, when I design a current source, I know that voltage, what VDS I am using, okay, is that clear? This will be close to VT, okay, so we say VT plus some as we call it, okay, so we know that value. Yeah, so best current source will be VDS larger than that, So at the edge it will be VGS minus VT is VDS, so we say VT. Okay. So एक VT drop है difference VGS minus VDS में, तो device saturation पर है, that's the criteria. तो थोड़ा सा उसके ऊपर रख देंगे तो saturate हो जाएगा. Is that okay? Analog circuits are only 10 to 20% of any mixed signal chip which you use, like a wireless mobile or any other. But if that 10 to 20% circuit does not work well, your 80 to 90% digital will fail immediately, because यही सब कुछ करने वाला है, समझे, front end है, all analog blocks are at the front end. If things go wrong at the input, everything is out anyway. So आपको आवाज किसका कुछ भी सुनाई दे सकता है या नहीं भी सुनाई दे सकता है. So remember, it is like saying this is the people who control everything in the world right now. Okay. Okay. So we have seen common mode. So let's look for the major interest for us is the difference mode. Common mode is very small. We are only trying to reject common mode signals. Fine. But amplifier is not for rejection. Amplifier is for amplification. So let us see what amplifications we get, and that is our major interest. So we do the same diagram once again shown here. If I say I have a difference signal of V in 1 minus V in 2, that is our difference signal. Two input signal का difference जो है वो difference signal है, V in 1 minus V in 2. Depending on if V in 1 is higher, VID is plus, if V in 1 is smaller, VID is negative, fair enough. But otherwise difference is always there. So I now play a game. I say I apply VID by 2 here and I apply minus VID by 2 the other side. So how much is the difference signal? VID. Is that clear? So when I say VID, alternatively I can also assume that the one of them is grounded and this input is VID. So VID minus 0 is still VID. So if there is a single input, the other input, this is what op amp is doing, and why I am showing you is this. Okay. Do you recollect that first circuit which I showed you? In most cases this is grounded, one of the terminal is grounded and you give input only at the other end. This condition is exactly what I am showing. One input is given here, the other input is grounded. So automatically input signal become different signals. This is what you actually do in op amps, equivalently saying this is what we are doing in a dip amp. Is that correct? I appreciate, I agree with you. Any day you do, यहाँ से यहाँ कुछ वोल्टेज मेजर करो, यहाँ से यहाँ वोल्टेज मेजर करो. यदि मुझे डिफरेंस सिग्नल लेना है तो हमेशा VID रहेगा, irrespective whatever way you do. The DC biasing is not controlled by this, DC biasing is only controlled through ISS. So I am not worried about the status of M1 and M2. So I am only interested to see VO1 minus VO2 divided by V in 1 minus V in 2. I never said anything more than that. It does not matter, as long as you take a different signal here, how does it matter? We are also taking a difference of VO1 minus VO2. You got the point? Irrespective whatever I do here, this will be different in two cases as you are saying, but the difference will come same. That is what we are trying to say. This is what superposition is trying to say actually. Now okay, you wait for this, I will show you. This is called, when the superposition is possible, this is called half circuit analysis. Circuit which I have shown you is called half circuit analysis, and when this is valid we will explain you when this is valid. If this potential is constant, this half circuit analysis is valid. There is a theorem for it. Okay. What you are questioning can be proved, okay, that this writing equivalent of half by 2 is equivalent of saying VID and 0. But so is the difference in the output voltage will corresponding to the values here and here. So if they change, so is this change. So difference will, as long as you are in linear, the difference will remain same independently. That is exactly what I am saying. What you are asking is what I am saying, it will always, this lower will change this, this higher will change this. The difference will be as much as saying one goes up, the other goes down. if this goes up, this goes down, so difference is same. As the condition I keep saying linear, as long as they are in linear situation, this will occur like this. If this is going higher, this will go low, this is equal, they are equal, then 0, that will come like this. Is that clear? So our assumption is not, if I say equal means what condition I am saying? Equal means common mode, yeah, output is 0. Is that point clear? In common mode, both sides VID by 2, yes, VO1 minus VO2 is 0. Otherwise one is higher, other is lower, or other way, depends on the sign. Is that clear? So essentially we are saying this is always valid as long as this voltage is constant. We will prove this point called half circuit analysis. Okay. Oh sorry, everywhere. Please now in onwards never ask me. Okay, I am very sorry. If I don't write to you, don't ask me unless I said it is single rail. You assume everywhere dual rail. Okay, is that point clear? What is the difference signal we are looking at? What she is questioning is very good, but what I am saying, if don't take half minus half, then one of them will conduct heavily, other will be smaller as they change. You change the polarity, still it will be opposite way it will move. Okay, so difference at the output will remain same independent way how input goes. The way input goes, so the output will shift corresponding. Okay, and condition is linearity is maintained. Okay, okay. By now logic, VRD is equal to VGS1 minus VGS2 because source is common. Okay, what is VID? VGS1 minus Vn1 minus Vn2, so which is VGS1 minus VGS2. If VID is positive, what does that mean? VGS is, your queries are now coming, your answers are now coming. If VID is positive, VGS1 is larger than VGS2. If VID is negative, VGS2 is larger than VGS1. Okay. In the first case, IDS1 will be larger than IDS2. In the next case, IDS2 will be larger than IDS1. Okay. जिसका भी VGS ज़्यादा है वो ज़्यादा करंट ड्रॉ कर लेगा. VGS minus VT का स्क्वायर है. So whichever has larger VGS will pull more current. Whichever has a smaller VGS will pull less current. So it can also occur for a given value of VID, the other transistor may switch off. Is that point clear? If I change VID, this other is opposite of that, so that becomes smaller and smaller, so that transistor may switch off, one of them. All the current will be drawn by only one side. Is that clear? If I change VID from say minus to plus, one of the transistor may actually go start drawing higher and higher current, the other will start reducing. At a given VID, the device, the other side may become off, all of the current will be picked up by the higher VGS ones, okay, all of it. That means when VGS2 goes less than VT, that transistor will be switched off. Whichever VGS goes less than VT, that transistor will switch off. Then the one which has larger VGS will draw all the current. Is that clear? All the current. So we may say whichever is fully on transistor, it will draw all ID. In the, let us say in the case VID was such that VGS1 is greater than VGS2 and VID is increasing, VGS2 is going down. So in that case IDS2 is 0 and IDS1 is equal to ISS. All the ISS is now flowing in that transistor. Is that okay? All of it is going through one arm. Okay. What is the condition I am using all this circuit? Please remember, if I add lambda here 1 plus lambda VDS, what will happen? This equation will become non-linear, okay, and then I will have to really do on the spice only and not analytically. I am not adding those terms because otherwise solving numerically is the only possibility. Is that clear? So when the problem you will solve in the tutorial which I am now giving next time, you first learn spice. And then that time lambda need not be 0. In fact, you do this analysis, put lambda 0 and put lambda 0.01 or 0.02 and see what difference it gives. It will give relatively sufficient difference, and that is one of our worries also. Okay. Is that point clear? If I change VID such that one VGS1 start increasing and VGS2 small, then VGS2 may go below VT, M2 transistor may switch off, all M1 will draw full current ISS. Is that clear? This is what, or vice versa can happen. If I make VID minus larger, then we say M2 will take all the current and M1 will become switched off. Okay, this is, yes, okay. So there will be some maximum minimum VID in which one of the transistor will draw full current. Is that correct? So let us wait for that expression. One can see from here, sorry, ये root आना चाहिए. If VID minimum becomes equal to minus 2 root VOV, VGS minus VT, we may say the transistor, let us say this is IDS1 and this is IDS2, maybe I should write this is IDS2, oh sorry, maybe IDS1, this is IDS2. So in minus M2 turns on, okay, and in plus M1 turns on. So यदि ऐसा है तो एक 0 से ISS जाएगा, दूसरा ISS से 0 के तरफ. Where they will meet? Which point? ISS by 2 point they will both VID by 2 and minus VID by 2 पर वो दोनों एक दूसरे के equal हो जाएंगे. Is that clear? This essentially is saying except for these ranges currents are not linear. Is that correct? Currents are not linear except for these ranges. So root 2 VOV minus to plus root 2 VOV में ही input signal यदि रहा, VID रहा, then only amplification in linear mode is, linearity is possible. So the limit of input for even different signal is there. Is that point clear? Earlier कौन सा बताया था मैंने? Common mode. अब मैंने difference mode को भी बोल दिया कि in between these two only values there is a linearity. And actually you should not come even closer to this. Why? Because if you come closer here there is no linearity. So actually it should be less than that both sides. Is that clear? Is that point clear? वहाँ at this curve they are not linear. So actually it should be away from the H points. What does that trying to tell you? Again small signal attitude आ गया उसमें. Do you get the point? If VID becomes larger, then what will happen? Only one transistor will operate and it will go into a saturation values, either minus or plus. Is that clear? So to remain both transistor in linear system, you should not exceed VID within this more than these two ranges. What does that mean? VID should be small values. So again difference amplifiers can only amplify if input different signals are small enough. Is that correct? So पहले बार में common mode का limit दिखाया, अभी मैंने difference का भी limit दिया. तो अभी आप ये क्यों हो रहा है? Because I have not shown you properly. This slope is very high. What is the typical slope of these lines? Do you know? Is the value of gains, open-ended gains is 10 to power 4 and above. So if you let us take a case, I have 1 millivolt signal. So how much will be output? 10 volt. Is that correct? 10 volt. If I have a minus 1, I have minus 10 volt. But power supply यदि 5 और 5 ही है, तो 10 तो जा ही नहीं सकता आपके पास. Is that correct? So even 1 millivolt difference signal may not be allowed if the gains are very high in the open-ended system. That means no feedbacks. Normal DFAM cannot take larger difference signals. Is that correct? Because the gains slope of these curves are very sharp, 10 to power 4, 10 to power 5. That is what we design in fact. So where do you think the larger gain will help you in the case of which circuit? Reaches faster to plus VDD or minus VSS. What is this circuit should be called? Fast comparator. Is that correct? Small change, output went to VDD or minus VSS. So output immediately you came to know whether it is plus or minus. So I have compared the signal as fast as possible. Is that point clear? If the slopes are very steep, the gains are very high, 10 by that value gain requires a very small change at the input. Okay. So if I say V in 1 is 0 or V in 2 is 0 and V in 1 is, what I am trying to say is this, which is interesting. Again you should know what I do in the normal case. Let us say this is my V in 1 and V in 2 is grounded. So if my input is something like this, AC signal, as this crosses 0, let us say this is 0, it will show minus value. If this crosses minus, it will show plus value instantaneously. Instantaneously means finite time, some nanosecond to microseconds. Okay. So faster the switch will occur when, so even with a small change over 0, it can show you an output going to 1 or 0 in some sense. Is that correct? Such are called fast comparators. Okay. So क्या condition होगी fast comparator की? कि they should have very high linear gains. Okay, high linear gains. अब gains कैसे बढ़ाते हैं ये अभी हम देखेंगे. How do we increase the gains? Okay, डिफैम का gain 10 to power 4 या 5 कैसे करते हैं. उसमें आपने देखा या कोई बीच में कोई स्टेज लगा है ना, तो इसका भी गेन कुछ होना चाहिए और उसके फॉलोड एक और स्टेज हमने लगाया है गेन स्टेज. ओके, जो इन दोनों मिलके वी मस्ट, और इवन देयर इज अ बफर, बफर डजंट हैव अ गेन फंक्शन, बफर इज ओनली going either to 0 or to 1, that means drive higher side or lower side, will show what is buffer. Otherwise this is how the gains will be very high. Is that correct? Very high. And that is exactly where op amps are used in such analog to digital applications. Is that clear? Why I am showing all this? Because most of the circuit, what did I say? They will be digital. Your inputs may come analog. So I want to give them outputs. Okay, ये लो मैं बताया क्या है. There where such circuits will be useful. Okay. Next time, first thing we will do, just we will first look into large signal operation. What does that mean? Larger signals. And then we will say what is the difficulty when I get a larger signal, and then how much smaller signal I should get, so that the thing which I said, I will first do a large signal analysis and then we say okay what is it creating, so okay reduce your signal to this value for good amplifiers. Is that okay? So next time start with large signal amplifiers. Please start reading into Cedra Smith, which chapter I don't know, जरा देख लो कौन सा है. Mass FET amplifiers is a separate chapter or bipolar, I don't know, I have not seen recently, but maybe in the same, So just look for this today's work, and we will start with large signal and finally we will give you DFAM. Is that clear? फिर मैं क्या करूँगा कि ऐसा एक मिरर बोलते हैं, बीच में ऐसा एक मिरर डाल दूंगा. यदि दोनों साइड सेम है तो इसको सॉल्व करो, उसको डबल कर दो, बस इसका डबल उसको कर दो, बस ऐसा उसको बोलते हैं हाफ सर्किट एनालिसिस. Actually, yeah, you have a point. Essentially, it's a small V OV is DC plus AC है, तो DC तो fixed ही है वहाँ पर. You got the point? That OV में OV are capitals. Okay. Essentially saying it is AC plus DC. तो DC value तो fixed ही है bias से. See you then.